In this video we're going to do a final summary of our entire algorithm for our adding and subtracting 32-bit floating point binary numbers. Now there's going to be 3 pages here. There's a page covering the general algorithm, a page covering addition and a page covering subtraction. So I'm not going to talk over this too much because we've seen this in the previous video. So this is the top level general algorithm. If we wanted to add or subtract 2 numbers, then we split the problem into 2. We did the absolute value, which is inside the bracket, and we did the sign, which is outside the bracket. The absolute value is going to be given by the modulus of the number x, the modulus of the number y, and whether we add or subtract will be dependent on the exclusive OR of the sign of x and the sign of y. So that's going to give us the absolute value of our answer. And the value out here is going to give us the sign. Now, we mentioned there was a complication that if the mantissa for the result, that is, if the value inside this bracket was actually a negative value, which is this option here and this option here, then the final sign for the result is going to be given by the complement of our sine of x and also the complement of our sine of x here. So we're not going to talk through this in any more detail. We've seen this before, and if you're unsure, you always go back to the original 2 videos for the algorithm. So let's move on and we'll look at our addition. So this was our overall addition algorithm. We said that we're going to compare the exponents for x and y, and we're going to ensure that ex is always greater than or equal to the value of ey. So this ensured that we didn't need to complicate our circuitry. So if we ensure that ex is always greater than or equal to ey, whenever we do the alignments in order to do the addition or subtraction, then we know we're always going to have to increase the exponent for the value of y, and we're going to have to decrease the mantissa for the value of y in order to make it equal to x. And we swap these round about in order to ensure that that's the case. Now we tentatively set the value for the final exponent as equal to ex, because that's the largest exponent value that we have here. We then go through the addition, and the addition is going to be the addition of the mantissas. So we take the mantissa for x, which is the larger one, and then we add on the mantissa for y. But as we said, the mantissa for y is going to be shifted in order to make it equal to the mantissa of x. Okay, so the exponent of y is going to be shifted to make it the same as the exponent for x. Therefore, we're going to have to decrease the mantissa by that same amount. We then go ahead and we can do the additions, and the final result is given by this mantissa r, which just stands for mantissa of the result. So the final result is going to be the mantissa of the result, which is the inside the brackets here, and it's the beta to the er, which is the exponent of the result. And the sign is going to be -1 to the sine of r. So what we have to do now is go through the normalization phase. Now we know that the mantissa for x is going to be a number that's greater than or equal to 1 or less than 2. Mantissa for y is a number that's greater than or equal to 1 and less than 2. So we're going to have 3 options whenever we add these numbers together. We're going to have option 1, where the mantissa of the result is a number greater than or equal to 2. Now in that instance, if it's greater than or equal to 2, then we're going to have to ripple the extra 1 through the exponent, so that is increase the exponent by a value of 1, and we're going to have to decrease the mantissa by that same factor, okay? So if we're increasing the exponent, it means we're actually increasing it by 1 means doubling it. So it means that to decrease the mantissa, we're going to have to decrease by a factor of 2, meaning we're going to have to half it. So mathematically, we would have the mantissa of the result divided by the beta and times beta to the exponent of the result plus 1. So we're rippling the 1 through and we're dividing the mantissa. Now the other option that we're going to have here is the mantissa for the result is greater than or equal to 1 and less than 2. So in this case here, we don't have any normalization required. It's already in a normalized format. So we're simply going to have the result MR times beta to the ER. Now the other option that we can look at here is option 3, where the mantissa for the result is less than 1, in which case we would get cancellation. But this is never going to occur whenever we are performing this addition, because we're never ever going to get a number that's going to be less than 1, because this number here is between 1 and 2, this number here is between our 1 and 2. Whenever we do the addition, we can never get a number that's going to be less than 1. So this just doesn't occur. So let's go ahead and we'll look at the subtraction algorithm. So for the subtraction algorithm, first of all, we wanted to look and see whether we actually had the subtraction button clicked. Now if that subtraction button is clicked, then we're going to have to negate the value of y. So if we had x minus plus y, that's the same as x plus minus y. So if this is the equivalent to having the button clicked on subtract, so when we're subtracting here, we just add on the negative. So we're going to have to negate the y value here. Now we have the other option where y is actually a negative, so we would have x minus y, in which case again we're going to have to negate this y to make it positive. So we're going to go through this negation here. Then we're going to again define the value for our exponent, which is greater or less. So we're wanting to ensure that the ex is always greater than or equal to ey. Again, we set the result tentatively to the exponent of x. We then go through the subtraction algorithm. Now in this subtraction algorithm, we're going to use our 2's complement. And what we do is we pick the smallest mantissa value and we all subtract the smallest away from the largest. And this ensures that this value in here is always a positive value. So it means when we get a positive 2's complement value at the end, the positive 2's complement value just looks like the normal binary value. And we also go through the process of making sure that the exponent for the value for y is the same as the exponent for the value for x. So we increase the exponent for the value for this value here, and it means that we have to decrease the mantissa by the same amount. So this is the shift of to ensure that both of these are able to be subtracted. So that's all to the power beta to the power ER. So the final result is MR, which is inside the brackets, times beta ER. And again, the final result, we have this here, and we have the sign dependent on -1 to the S sign of the result. Now again, we're going to have to normalize the result, and we're going to have 3 options. So in this case, we'll have mx minus my as mr, which is just what's inside this bracket. And we know that mx, the number that comes in, is a normalised number, so it's greater than or equal to 1 and less than 2. The my, which is our original number that comes in, is normalised, so it's greater than or equal to 1 and less than 2. So again, we've got 3 options here. We could have mr greater than or equal to 2. So in this bracket here, greater than or equal to 2. Now, that can't actually occur whenever we're subtracting, because we're going to have a number between 1 and 2 and a number between 1 and 2. So whenever we subtract one from another, we're never going to get a number that's greater than 2. So this option just doesn't occur. We're going to have another option here where the result is actually the normalized result. So it's a number greater than or equal to 1 less than 2. So in that case here, the answer is already normalized. So there's no further requirement to change the answer. We just have our answer MR beta to the ER. Now, the interesting thing to note here is that this option here will only occur when the exponent difference is greater than a value of 1. So we'll see that in the next video when we look at the actual building the architecture. Now, the other option here is option 3, and that is when we have the cancellation. That is when the mantissa for the result is less than 1. So when the mantissa of the result is less than 1, what we can do is we can count the leading zeros for the mantissa, and then we can change the final result. So what we do is we increase the mantissa for the result to ensure that it's a value between 1 and 2. And in doing so, we're going to have to decrease the exponent by that same factor. So the exponent is going to be beta to the ER minus lambda. Now, the interesting thing about this one here is that this leading zero count and the cancellation will only occur whenever the exponent differences are a value of 0 and a value of 1. Now, we did look in the previous video and we've seen whenever we had a difference of 0, whenever we did the subtraction, but we could have a difference of 1. So let's just quickly have a little look at an example here, which we can show. So in this example here, we have 8 minus 7 is equal to 1. So the exponent difference is a difference of 1 here, because 8 can be written as 1 times 2 to the 3, and the minus 7 can be written as minus 1.75 times 2 to the 2. So you can see there's an exponent difference of 1. So these are just out of range, meaning the 8 is in the lower part of the range, and the 7 is in the higher part of the previous range. So whenever we subtract them, we can get cancellation. And in this instance here, what we have to do is we have to increase this by a factor of 2, so that goes 2 to the 3. We're going to have to decrease this by a factor of 2, so it goes to minus 0.875. We've now got the same exponents. We can do the subtraction, and that gives us 0.1525 times 10 to the 3. And you can see here we have actually got cancellation, so it means that the value for MR is less than 1. So in order to ensure this number becomes a value between 1 and 2, that is normalising it, we would have to double this once to get 0.25, double it again to 0.25, and double it a third time to get a value of 1. So when we double that 3 times, we're going to have to therefore take away the factor of 3 from the exponent. So we're going to have this number here has been doubled 3 times to get a value of 1. So it means that this number here will have to go down by that factor of 8. So we're going to have 10 to the 3 minus 3, so it's 10 to the 0 is a value of 1. Okay, so that is just an extra proof that we can have a leading zero count and cancellation whenever the exponent is a difference between 0 and 1. Now, these little extra bits of information that we have here about the exponent differences, these are quite important. And what we want to do in the next video is we want to take this addition and subtraction algorithm and we want to create an architecture that is going to have a minimum latency. That is, we want to have an architecture that has that allows us to run certain operations in parallel, and then from running the operations in parallel we can then choose the actual result that we require. So this is going to cut down the time it takes to go through the actual algorithm. So there's redundancy built into both the addition algorithm and the subtraction algorithm, and we want to make sure we take advantage of this redundancy. So we'll get onto that in the next video, and we'll create an architecture, and it's called the dual path architecture, and it splits the addition and subtraction into two different paths dependent on whether the exponent is a value of 0 or 1, and that would be called the close path because the numbers are close together, and the far path, which will have an exponent difference which is greater than 1. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.